So let's look at the case of a gun which has been bore-sighted on its target. Bore-sighted means that the gun has been pointed at the target and then someone has looked through the barrel to establish the point of aim. So let's imagine that this is our horizontal distance. Here's our barrel. Now this is the line of sight through the barrel to the target. So this is the point of aim. And we would like to know where is the point of impact. Because we know, of course, that as the bullet flies, the projectile flies, it will drop the whole time it's traveling through the air. So if we make a vertical plane here, let's imagine that we're shooting at a wall or something. And we'll say that the point of impact is a distance y down the wall. Let's find out what it is. So the solution, as you probably know, is to say, this is distance d. Let's say it might be something like 150 meters. And we fire the gun, and at the instant that we shoot, the velocity vector v is only in the x-axis. So because we're shooting in the horizontal direction, v equals vx and vy equals 0. The solution to most projectile problems is if you can find how long the projectile takes to get to the target, then you can use that amount of time knowing that the bullet or projectile, whatever it is, will be falling for that time at an acceleration g towards the ground. And so we know very well that the projectile will have a motion like this if we ignore air resistance. If air resistance is included, then the projectile slows down as it travels at a rate that's proportional to its velocity, and this solution wouldn't be valid anymore. So we're going to assume that we can ignore air resistance. So the first hint is to find the time of flight. Which is easy enough to find. So we know that speed is distance over time, which tells us that the time to get from here to here is d over v, the distance d divided by vx. So this is very important because this equation is valid no matter where the projectile is aiming, even if we're aiming uphill or downhill. If we know the x component of the initial velocity and that remains constant, and if we know that dx is the distance along the horizontal direction, then this will always be true. So let's say that this is always true. It's a handy thing to remember. So now, having got that, we could now find what is the distance that the projectile will fall in that amount of time. So one way to look at it is to use the kinematic equation for motion at constant acceleration, which says that y will be equal to y0, the initial position, plus vy initial times t plus 1/2 gt squared. So this is our kinematic equation for constant acceleration. So let's put in some terms. So y0 is 0. Let's assume that this here is 0 and that we're measuring the positive direction down here. So y is 0. Is there any initial vertical velocity? No. So all we have is 1/2 gt squared, 1/2 g dx over vx all squared. And that's the answer, and that's all there is to it. So that's pretty easy. Okay. Let's imagine that we actually had a known velocity for this projectile or this gun. Let's say that it was 1,000 meters per second. Then we can find that y in this case is 1/2 times 9.81 times dx, which is 150 meters, divided by 1,000. And then that's all squared, and that's going to give you your answer. So the answer for that is 0.11 meters, or 11 centimeters. So that's the distance that the bullet drops as it travels along its trajectory in this case.